Greetings and welcome to Mr. Van Lowe's poorly monetized low budget science channel. Do not click like. Do not subscribe. Okay, today we're going to take a look at topic 3.1. It is titled Thermal Concepts. I had to break this into two lessons even though it's not that long. There's just a lot going on. Okay, so your learning objectives for lesson 1 will be to describe temperature in terms of internal energy. Okay, so by the end of this lesson, you'll be able to do that. You will also be able to use Kelvin and Celsius temperature scales and convert between them. Okay, now these are only two learning objectives, but there's actually quite a lot to cover here, so let's jump in. First, let's talk about matter. Matter is made up of tiny particles called atoms. You're probably familiar with this. These are the most easily divisible unit of matter. We can break them down further, as we'll see a little bit later. They're made of protons, which are positively charged, neutrons, which have zero charge, and protons and neutrons are composed of particles called quarks. We'll look at those again in topic 7. Yep. Atoms can chemically bond, form larger molecules or ionic structures. Again, this is all stuff you're probably familiar with. Our chemical bonds are due to the wacky behavior of electrons, and electrons are negatively charged particles. These are considered fundamental particles. That means we can't split them, at least as far as we know currently. Okay, so the particle model of matter is really important because if we can think of matter in terms of these particles, then we can explain its behavior. Okay, so very useful. Our particles can be either atoms or molecules. Sometimes you may hear me describe a ball as a particle. It's just a kind of a useful way to think of things in physics. So we'll often diagram our quote-unquote particles, and they look like spheres, but in terms of molecules, water doesn't actually look like a sphere. It has a more complicated structure. But we like to simplify things in physics. Okay, so let's take a look at solids here. I'd like you to think about the characteristics of particles in a solid, and if you want to, you could pause the video. You don't have to. I could hum the Jeopardy theme song, dun, 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 but I could not. Anyway, let's move on. So particles are fixed relative to each other in a solid, and that means they're constantly moving. They're constantly vibrating. They're constantly undergoing, in fact, oscillations. Richard Feynman referred to this as jiggling, which is not a bad way to think about it. Chemical bonds can be modeled as springs between particles. And that means that you can actually use Hooke's law to model these forces acting between particles, which is pretty cool. So this is not a crazy way then to think about matter, where these springs are chemical bonds, and these particles are just constantly moving. You can actually buy models that look like this. They're a little bit problematic because our lattice structures aren't usually cubic. They're usually hexagonal, have 3 or 4 bonds. But anyway, moving on. So here we have a graph of potential energy, and we're looking at the distance between our particles. And there's no unit here because we're just kind of checking out the idea. So this dip in the graph here is showing the smallest possible potential energy between particles. Okay, so in other words, what's happening here is our forces are balanced at this point. It's called our equilibrium position, and we'll see that more in topic 4 and topic 9. So at this equilibrium position, the attractive and repulsive forces are balanced. They're equal. They're in equilibrium. Okay, so if we move our particles closer together on our chart, in other words, in the direction of this blue arrow here, then our springs are going to be compressed and the particles will be repelled from each other. If we move them farther apart from each other, if we extend our particles away from each other, if I try to pull this little ball in this direction, then the particles will be attracted to each other. We'll have stretched our springs out. Because our particles are actually jiggling, they're moving constantly, they're always kind of compressing and extending. And you could think of this as an oscillating mass on a spring, which we will do on topics 4 and 9, although not using this particular model just because things get a little complicated. We'll simplify things in topic 4 and 9. Topics 4 and 9. Don't worry. All right, temperature. When we add energy to a substance, the kinetic energy of the particles will increase. And temperature is directly proportional to the average kinetic energy of the particles of the substance. We'll look at this further in topic 3.2. Because kinetic energy is proportional to velocity squared, we can infer that velocity of the particles is going to increase with temperature. And they do. So they start jiggling harder. They start moving more. And that's going to be important here in a second. Okay, so you've got your ball here, and it starts jiggling more and more, and it's jiggling more and more violently, and eventually, if it jiggles hard enough, it's going to break these chemical bonds, and this particle is now free to move around more than it was before, okay? So, it doesn't mean all the chemical bonds are gone, but we're going to get these new and weaker chemical bonds forming, and you'll cover this a lot in IB chemistry for those of you who are taking both physics and chemistry. So our particles are going to remain stuck together in this new system, but they'll no longer be in this lattice structure, okay? They'll be moving more, they'll be rolling against each other, and what we now have is a liquid where our particles are no longer locked into this position relative to each other. Okay, so if we continue adding energy to the system, our weaker bonds will eventually also break, and then the particles are going to be completely separated. These gas particles are now going to contain a large amount of kinetic energy, and we'll look at that in more detail in topic 3.2. And we'll actually look at this process of our bonds breaking a little bit more in our next lesson for topic 3.1 as well. Okay, so now we've covered solids, liquids, and gases. We also have plasma. Plasma is a fourth state of matter, and students always ask me about plasma, and I'm always like, I don't really want to talk about it because as cool as it is, we just don't need it for IB physics. But it is cool. So it's primarily composed of charged particles, ions or electrons, and plasma is a good conductor. And that is one of the reasons why we see plasma on Earth in the form of lightning bolts. So the light that you see is due to plasma emitting energy. We also see plasma in neon signs and these cool little plasma balls that you can find in gadget stores at the mall. So check them out. They're awesome. Although there's not a ton of it on Earth, plasma is actually the most abundant form of matter in the universe. We typically find it in stars, though. We don't really deal with it, as I said earlier, because the transition of matter to and from plasma is a little bit complicated, and we keep it simple in IB physics, usually. Okay, a little more about temperature. We measure temperature in degrees Celsius or Kelvin. We do not use the F word, Fahrenheit. Don't do it. So we could do it, but then we have to use conversion factors and it gets annoying. So we don't use Fahrenheit. So a change of 1 Kelvin is equal to a change in 1 degree Celsius. When we're looking at changes of either of these, they're basically the same thing. Okay. It's only where we start talking about the coldest possible temperature that we differentiate between a Kelvin and a degree Celsius. So 0 Kelvin, or what we call absolute zero, is negative 273 degrees Celsius. So this tells us our conversion formula, and here it is. So temperature in Kelvin is equal to temperature in degrees Celsius plus 273. Okay, so if you want to convert from one to the other, you can use this formula, and that's all you need. We can never actually reach absolute zero because our particles would need to contain zero kinetic energy, and that's just not possible. Okay, we can get incredibly tiny temperatures in a lab, though. Actually, lower temperatures than you would even find in deep space, which is kind of cool. All right, so measuring temperature is done with a thermometer. And so analog thermometers are just these glass tubes. They're full of liquid, and our liquid will either expand or contract with changes in temperature. So if you heat up the liquid, it expands. If you cool down the liquid, it contracts. Okay, so if you want to calibrate this gas tube, you put it into distilled ice water, preferably at sea level, and that's going to be at 0 degrees. So you would then mark your tube at the level of the liquid inside it. Okay, you would then take that tube and put it into boiling distilled water, preferably at sea level. And this should have a temperature of 100 degrees Celsius. So the liquid expands, and then you mark the tube again. So now you have 2 marks on your tube, and you just need to divide those marks by 100 in terms of distance, and then add a bunch more marks to the tube. Okay, and there's your thermometer. Done. Okay, internal energy. So this is important, more important than your thermometer. So internal energy, our particles of matter contain kinetic and potential energy. So whenever you have a substance, it's going to have both of these things. Okay, so internal energy then is given as the sum of both kinetic and potential energy of the particles of a substance. So, few key points. Temperature is only related to kinetic energy. That's it. So the potential energy stored in the chemical bonds of the substance, they don't matter. Doesn't matter at all. Doesn't matter for temperature. Potential energy is stored in chemical bonds, and this is unrelated to kinetic energy. Okay, so these are two totally separate things in terms of the energy that we put into our substance. Critically, different chemical bonds will store different amounts of energy. And so this is why different substances have the ability to store different amounts of energy, which we're going to look at in more detail in our next lesson. Okay, so if I add the same amount of energy to 2 different substances, I'm going to get 2 different temperatures, which, if you think about it, is kind of crazy. And that's going to do it for this lesson. So my sources for this lesson are right here. As always, Physics for the IB Diploma by K.A. Tsokos. I used Wikipedia extensively for topic 3.1, but only this one for this particular lesson. Throw Wikipedia some money if you get a chance. They're awesome. Do not click like, do not subscribe, but do have a great day, and thanks for watching.